Welcome back to the Quantum Rings Quantum Summer School. Today, we're going to be learning about the Quantum Fourier Transform. We're going to start by covering the classical Fourier Transform and getting an intuition for that. Then we'll move on to the Quantum Fourier Transform, and finally, we'll put it into action to perform the quantum phase estimation algorithm. Let's go. So what is the Fourier Transform? The Fourier Transform is just a function which transforms a signal between two different domains. So what do I mean by domains? Well, one common example is the time domain and the frequency domain. So for instance, you could have a signal that looks like this, where the amplitude is just varying sinusoidally over time, and this signal has some frequency component to it. So the Fourier transform would pick out the frequencies that are present in the signal. So in this case, if we perform the Fourier transform, we'd end up getting like a single spike at the frequency of that sine wave. Another common example that you may hear about for Fourier transform is position and momentum space. And a good example that I would like to use for this is an electron. So an electron is a quantum mechanical particle, and quantum mechanical particles don't have a definite notion of properties. Just like a qubit, an electron doesn't have a definite position or momentum. It has some wave function that is a superposition of positions and momentum. And there's kind of a notion of uncertainty between position and momentum. So for instance, if you're pretty sure about where your particle is, your electron, your wave function is sharply peaked around some value of x, then you're going to be pretty unsure about the momentum of your particle. And conversely, if, for example, you're pretty certain about the momentum of your particle, then you'd be pretty uncertain about the location of your particle. So the Fourier transform just gives us a way to transform between these two related spaces when there's some notion of uncertainty between them. So just like we can do the Fourier transform, we can also invert it and do the inverse Fourier transform. And this would just take us in the opposite direction. So normally we would think of the Fourier transform as taking us from the time domain to the frequency domain, and the inverse Fourier transform would take us from the frequency domain to the time domain. So for example, you could have something in the frequency domain that looks like a sinc function. I'm not going to draw it very well, but something like this. And then if you perform the inverse Fourier transform, this is just a square pulse. And the reason that it kind of looks like this is because a square pulse is actually composed of many frequencies. A square pulse is just many sines overlaid on top of each other. And as you add increasingly more sine waves, you can start getting things that look like this. And as you add higher and higher frequency sine waves, you'll eventually converge to the square pulse. So that's why these tails are going out to infinity. So there are many applications for the Fourier transform. I'm going to list a couple of examples, but this doesn't even really scratch the surface of what it can do. It's a very powerful tool. So one example is for audio signal processing. You can take sound bites and find the frequencies that it's composed of, and this can help you identify phonetic sounds in speech. Also image processing, so for instance image compression or edge detection, these are a type of things that use Fourier transform. Also for like MRIs or EEGs or ECGs, you can use a Fourier transform to identify, for instance, abnormal rhythms in a heartbeat. And then also in quantum computing is super useful. Just in general, because the Fourier transform detects periodicity or some frequency component in a signal. And so it's useful for a lot of quantum algorithms, including Shor's algorithm for factoring large numbers. And today we're going to use quantum Fourier transform to perform quantum phase estimation. So basically we're going to use the quantum Fourier transform to detect the phase of a unitary operator. Let's start off by just talking a little bit about the math behind this. So for the classical Fourier transform, we have some vector x, which has all of these components, x0 through xn minus 1. And these could be complex numbers. And then when we apply the Fourier transform, we get some new vector y, which has components y0 through yn minus 1. And these are given by the following formula. And you can just take this as a given. This is how it works. This is also just the discrete version of the Fourier transform. There's also a continuous version where you have an integral instead of a sum. But for the case of quantum Fourier transform, we're only going to be working with the discrete version. So I'm only talking about that today. So I just want to point out this term here. So we have this e to the minus 2 pi I kj over n. And just to give a sense of what this is, I want to talk about how we would think about this term, which is e to the minus 2 pi ij over n. And j, remember, is the indices which range from 0 to n minus 1. So let's just look at these in the complex plane. So one example we could have is n equals 3. The first term, or the first one, would be e to the 0. E to the 0 is just 1, so that's just this vector pointing here. Then we have the one e to the minus 2 pi I 1 over n. And that's going to put us at an angle of minus 2 pi over 3. So, and this is e to the minus 2 pi I times 1 over n. And then if we do this again, we would get another rotation of minus 2 pi over 3. And this would be e to the minus 2 pi I times 2 over n. You can do this for any n. So if you did it with n equals 5, then there would just be 5 of these here. And the rotation between would be 2 pi over 5. I'm not drawing this the best, but you can get the picture. So basically, these terms are kind of like spokes on a wheel. And one thing I want to note here is that if you sum up all of these vectors, you're going to get 0. Because all the vertical components cancel out and all the horizontal components cancel out. So we can also do the inverse Fourier transform. And it turns out that the inverse Fourier transform is really similar to the Fourier transform, with the main difference here being that instead of a minus sign in the exponent, we have a plus. And one question you could ask is, well, what is the inverse Fourier transform of the Fourier transform of x? So here's our inverse Fourier transform, and we'll call the Fourier transform of x y, and then this final thing will be z. And let's consider the element zk. So we can just plug in our definition of the inverse Fourier transform, so writing zk in terms of a linear combination of yj's. And then we can plug in what yj is in terms of a linear combination of xm's. So this is just coming from our Fourier transform. Then we can rearrange some terms, so I'm just combining everything together, pulling this xm out front and the sum over m. And then we're left with this, where we have a 2 pi ij times k minus m over big N. And I want to point out that this is an integer. And we talked about before how this sum is always going to be 0, right? Because it's like spokes on the wheel in the complex plane. But there's one case where this is not true and it doesn't all cancel out. Can you think of what it is? So if k equals m, then k minus m is 0 and e to the 0 is 1, and that sum would then equal n. So basically this whole term is going to equal 0 if m is not equal to k, and n if m is equal to k. So we can express that in terms of a delta function. So this delta function literally just says this is 1 if m equals k and 0 else. And so all of the terms in this sum are going to be 0 except when m equals k. And so in that case, xm will just be xk. So we have that zk equals xk, and we've got back to the same thing. So the inverse Fourier transform just cancels out the Fourier transform as like the identity. Now we can move on to the quantum Fourier transform. So now we have, instead of vectors, we have kets, or quantum states. So here's an example of a quantum state. We have x, and then x is going to be a linear combination of all the bit strings of length n. So this here, this capital N, if there's n qubits in our system, then n is going to be 2 to the little n. So for example, we could have our x be something like 1 over root 2, 0, 1 plus 1, 1 if we had little n equals 2 qubits. When we apply the quantum Fourier transform to a wave function, what's going to happen is the amplitudes in front of the basis vectors are going to receive a Fourier transform. So when we take the quantum Fourier transform of x, we get some ket y, and this is also just a sum over all the basis states. But now this coefficient cyk is going to be the Fourier transform of the coefficients of x. One question you could ask is, well, what is the inverse quantum Fourier transform? And think about what would you do if you wanted to undo a unitary operation that you've done. And the QFT is a unitary operation. The inverse of a unitary operation is its Hermitian conjugate. So IQFT is just QFT dagger. And if we were to write it out in this way, then we would find this instead. And again, the only difference here is this minus sign. And one thing I want to point out is just by convention, we have this minus sign here in the inverse quantum Fourier transform, but classically, that minus sign is in the Fourier transform. So it's kind of backwards from what you might expect, but that's just the convention. Okay, so we've written down mathematically what QFT is, but how do we construct an algorithm or a series of gates that does it? So just to reiterate again, this is the action of the quantum Fourier transform. And this capital N here is 2 to the n, where n is the number of qubits. And this here is just some arbitrary state because we have some linear combination of all the basis states. The basis states being the bit strings of length n. And then here I can just literally plug in what cyk would be. This is a lot, so in order to understand this better, we're going to simplify and we're going to take just one basis state to look at. So here's our basis state, x, and we'll say x is x1, x2, all the way through xn, and then each of these is going to be 0 or 1. So for example, x could be 1, 0, 0, 1, 0 if we're working with 5 qubits. Then the quantum Fourier transform is going to be as though only one of these amplitudes is non-zero, and it's 1. So we can just write down what we would get in that case. So we would have 1 over root 2 to the n, maybe just to be a little bit clearer, I'll replace this one as well. And we'll be summing over all the basis states, k, with this factor out front. And we see that we have 2 pi I xk over 2 to the n. So let's just write out exactly what this is. So first we have the state k equals 0. This is the all 0 state, and we're raising e to the power of k. So that's just going to be 1. So we have the all 0 state. Then we have the state k equals 1. So that's going to be the state that's like 0, 0, 0, etc., 1. And that's going to have the factor e to the 2 pi I x times 1 over 2 to the n. The next one would be 2 pi I x times 2 over 2 to the n. And that would be for the state k equals 2. You can keep going like this all the way to the last term, which would be e to the 2 pi I x 2 to the n minus 1 over 2 to the n. And this would be the state k equals 2 to the n minus 1, and that's the all 1 state. So we have in every single term this factor k over 2 to the n. So let's understand better how to express this. So let's start with 0. I'm going to write this in a way that may seem silly at first, but it's going to be helpful. So we can express 0 over 2 to the n as 0 over 2 plus 0 over 4 plus all the way to 0 over 2 to the n. What about 1 over 2 to the n? Well, this would be 0 over 2 plus 0 over 4 plus 1 over 2 to the n. And we can keep going in this manner. So 2 over 2 to the n for this one, we would need 2 over 2 to the n minus 1. Wait. That should be a 1, not a 0. Okay. 3 over 2 to the n would be 0 over 2, 0 over 4, 1 over 2 to the n minus 1, plus 1 over 2 to the n. And you can keep going all the way up to 2 to the n minus 1 over 2 to the n. And this one would be 1/2 plus 1/4 plus all 1's in the numerators up to 2 to the n. So now I want to just look at something here, which is all the numerators. So for the case of 0 over 2 to the n, you have 0, 0, 0, all zeros. For 1, we have 0, 0, 0, all the way to just a 1. For 2 to the n, we have 0, 0, 0, all the way to 1, 0. Here we have 0, 0, 0, all the way down to 1, 1. So we can see that these are actually just building up whatever k is in binary. And then here we have the all 1 state as well. Okay, so essentially what we can see from this is that whenever the first qubit is in the 1 state, we should apply a factor of 1/2. And whenever the second qubit is in the 1 state, we should apply a factor of 1/4, and so on and so forth. We can reconstruct QFT of x in terms of a tensor product. So for the first qubit, if it's 0, there should be no phase. And if it's 1, we should end up getting the phase e to the 2 pi I x over 2. Then for the second qubit, if it's 0, we shouldn't add any phase. But if it's 1, we need to add the phase like 2 pi I x over 4. And we can keep doing this all the way to the last one. So just to emphasize again, in the way that we've expressed this, we're reconstructing k, and as we reconstruct k in the exponent, we're picking out whether that qubit should be 0 or 1. So just to give a quick example, if we had the case of just 2 qubits, then we'd have QFT of x is 1 over 2 to the n, 0 plus e to the 2 pi I x over 2. And in this case, for instance, if we have the state 1, 0, that's going to come from picking out this phase and this phase, which is none. And we're going to have the coefficient in front of 1, 0 in the end is going to be e to the 2 pi I x over 2. But then, for instance, if we have the 1, 1 state, the final phase in that is going to be e to the 2 pi I x times 1/2 plus 1/4. This is reconstructing k over n, because in this case, k is equal to 3, 1, 1 is 3, and then n is 2 squared, which is 4. Same thing here. Here, k over n, k is 2, and n is 2 squared, so this is 1/2, and that's also what we see. So now I want to introduce a useful notation, which is a binary fraction, and I'm just going to express it here with square brackets, so 0 dot and then x1 through xn, where x1 through xn are all either 0 or 1. So for example, this could be something like 0.1101. And this is just going to be a sum over those elements times increasingly large negative powers of 2. So for this example, this would represent 1/2 plus 1/4 plus 0 over 8 plus 1/16. And that's it. But it could also be longer. So for instance, if we had more qubits and there was just more zeros, you would just have keep adding 0. So I don't know exactly what this is. We can check quickly, but so this is just a very compact notation for writing down sums of ones and zeros divided by powers of 2. It doesn't have to be less than 1. What we're working with today is mostly going to be less than 1, but you can also do other ones. So for instance, 5/2. We have our expression for 5, which is 101, and usually the decimal place would be at the end. We're dividing by 2, so we move it one place up, just like dividing by 10 in our normal number system. And then what we're left with here is 10, which is 2, and 0.1, and this is 1/2. So this is 2.5, as we'd expect. Just to emphasize, for instance, if we had 5/4, then this would be 1.01, and this is 1. And this is going to be 0 over 2 plus 1 over 4, and this would give us 5/4, just like we expect. So now we can take our expression from the quantum Fourier transform before and rewrite it in terms of these binary decimals or binary fractions. So remember what it looked like. This is just x over 2 because the decimal place moved 1 point over. This is x over 4, so on and so forth. And then one thing I want to point out here is that 2 pi I, e to the 2 pi I times an integer is always going to be 1. That means you've made some integer number of full circles in the complex plane, and you'll end up back at 1. So we can essentially chop off everything that's before the decimal point. And what we're left with is this. And this is our final expression for what the quantum Fourier transform does. And I just want to emphasize here that this is going to be our most significant bit, and this is going to be our least significant bit. I'm just emphasizing that here because when we write down our quantum circuit, this is going to be our most significant bit is actually going to end up at the bottom wire, and the least significant bit is going to end up on the top wire. So let's talk about what happens to the kth qubit during the quantum Fourier transform. So we said that we could express the action of QFT as a tensor product. So that means that we could write it as n unique steps, where first we apply the unitary to x1, then we apply a unitary to x2, so on and so forth all the way to n. So we can consider the kth one, and after we apply that, all of the other qubits would be unchanged, and only xk would be changed. And it would change in this way that we found before. So there's a few things that we can notice about u of k. So first of all, we can see from this decimal here that uk does not depend on x1, x2 up to xk minus 1. It only depends on xk through xn. We can write down what this is. So in the exponent we have 2 pi I times this decimal, and we can just expand this out in terms of fractions, 1/2, 1/4, and so on. And then we would end up getting this. So we have pi I times xk, and then we'd have xk plus 1 over 2, so on and so forth, all the way to xn over 2 to the n minus k. We can consider what happens depending on what xk is. So if xk is 0, then this first term is going to be 0, and we can re-express this part as a new binary fraction because we added in a factor of 2, so that shifts everything up by 1 point. So here, that pi I xk, pi I times 0 is 0, so we get no phase. But if xk was 1, we'd have that extra factor of e to the I pi, which is minus 1. So what should we apply to xk in order to make it have this behavior? So this looks very similar to the Hadamard gate. So that's actually all we need to do on the kth qubit directly. And then the rest is going to depend on the k plus 1 through nth qubit. So then the last thing I want to point out is for every index greater than k, if that bit is non-zero, then we want to apply a phase of pi times xm over 2 to the m minus k. Actually, I'll just make this easier because we said if xm is 1. So this is just a controlled phase gate. There's a lot of indices here flying around. It's a little bit confusing, but I'll write out a concrete example. So for instance, here we have n equals 3. So for x1, we're going to apply a Hadamard gate, and then we need to apply a controlled phase. So do rotation of pi over 2, and that's if and only if x2 is 1. And then we have another gate, which is a pi over 4 rotation, if and only if x3 is 1. So just recall that this is coming from that decimal with a factor of pi in front of it. And then for x2, again, we're applying a Hadamard gate. And then here we would have that binary decimal. So we just need to apply a controlled phase of pi over 2 controlled on qubit 3. And lastly, qubit 3 just gets a Hadamard gate. If we want to do the inverse quantum Fourier transform, all we have to do is take the Hermitian conjugate of that. So for that, we just flip the order of all of the gates and take their Hermitian conjugate. So Hadamard is its own Hermitian conjugate, but for a controlled phase rotation, we would need to rotate in the opposite direction. So minus pi over 2, minus pi over 4, etc. Now let's move over to the coding notebook. So I have it pulled up here. We're on the first cell to import the libraries that we need. And then we also have some helper functions here to convert decimals to binary fractions and binary numbers to integers, etc. So first let's talk about the classical Fourier transform, and this is mostly just to give you a feel for it if you haven't seen it before. So this will give you a chance to play around with different signals and what Fourier transform looks like. So for instance, we could make a sine wave. So this would be in the time domain, and then we want to apply the Fourier transform to see what it looks like in the frequency domain. So we can have some frequency in hertz, so maybe we want 5 hertz, and we're going to measure for 3 seconds with 100 samples, and our signal is just going to be a sine wave at that frequency. So here's what our signal would look like. And then we can apply the Fourier transform to this. We can just use these functions from SciPy. And the Fourier transform looks like this. And you can see everything is 0. And then we have 2 peaks at 5 and minus 5. So actually, every time we do the Fourier transform, we would have this duplication. It's going to be mirrored over 0 because plus or minus frequency is essentially the same. So we can just plot the positive half. So this makes sense because we're basically 100% certain about what the frequency is. We have just a single tone in our signal. We could also make a signal which is a sum of 2 sines. So here we're going to do a sum of one frequency and another frequency. So maybe now I want 20 hertz and 7 hertz. So here would be our signal. And maybe to us, we can't really tell exactly what's going on here. But if we apply a Fourier transform, it can pick out those frequencies in the signal. One thing that you might notice here is I said, okay, we're going to have 7 hertz and 20 hertz. And here we picked up on the 7 hertz, but we haven't picked up on the 20 hertz. And one of the reasons for that is we have to be careful about the duration of measurement and the number of samples. So we can actually increase the number of samples. So if we make this 200 instead, now we can actually see into higher frequencies. This makes sense because if the distance between your sampling points is too high, you could miss higher frequency signals. We can also change the relative amplitude of the 2 sine waves. So maybe I want 4 and 6. And here are 2 sine waves, and I want to amplify the one at 4 hertz, make it twice as big. Then that component, that frequency signal in the Fourier transform is going to be stronger. So if you want to explore this further, here's a few questions you can think about. What happens if you increase or decrease the duration of sampling, increase or decrease the number of samples, and then what is the relationship between these two? In real life, we don't actually have perfect sine wave signals, so we have a lot of noisy data instead. So we can add some random normal noise on top of our, on top of our signal. So I'm going to do random normal noise with a mean of 0 and a standard deviation of, let's say, 0.1. And I want this to be the same length as x. And then I'm just adding that noise on top of our signal. So here's what our signal would look like. And here's the Fourier transform of that. And you can see now that we don't have a perfect 0 apart from the frequency that we're looking for. And that's because this noise has added some more uncertainty in the frequency in the signal. And if we were to increase this noise, so let's say 0.5, then the signal in the frequency domain would become even more noisy. So if you want a challenge problem, you can make a signal which is a square pulse. So it's 0 everywhere, and then it's 1, and then it's 0 again. You can see what the Fourier transform of that looks like. So now let's move on to QFT. So we already saw in the previous part how to construct the quantum Fourier transform. So let's just do this together. We know we need to go through each of the qubits one by one, and then we apply a Hadamard gate, and then these controlled phase rotations, which get increasingly smaller phases, so pi over 2, pi over 4, pi over 8, etc. So let's say we have 3 qubits. I want to loop through all of our qubits. First thing we want to do is apply a Hadamard gate. And then we want to loop through again. And we want to start with I plus 1 and go all the way up to the number of qubits that we have. And what we want to do is we want to apply a controlled phase gate. So we can do that with CP. And the phase is going to be pi divided by 2 to the, I minus j. And we want to apply that controlled on qubit j and targeting qubit I. And then I'll just add a barrier here in between the different qubits so it's easier to tell them apart. Let's check that we did this correctly. Okay, so I can already see that I mixed up my i's and j's, so I'm just going to change this around. Okay, so now we have the same thing as the picture above. We have our Hadamard gate. We have a controlled phase of pi over 2 and then pi over 4, and then continuing like that for all the rest of the qubits. We can make the number of qubits bigger so you can see that pattern continuing. So now let's package this up into a nice function that we can use later. So I'm going to grab this section here and paste it into this function. And again, just to double check, we can make a quantum circuit, and then we can use the compose function to place that circuit into this circuit. And we use in place so that it modifies this quantum circuit object rather than creating a new one. Okay, what about the inverse quantum Fourier transform? Well, all we have to do is take the Hermitian conjugate, and we can do that pretty easily by just using inverse. And now we can see our inverse QFT. And it's just exactly the opposite. So we flip the order of all the gates, and we take the Hermitian conjugate of each gate. So H is its own Hermitian conjugate, but then for the controlled phase rotations, we need to rotate in the opposite direction. Okay, we've built our quantum Fourier transform, and now we want to use it to do something useful. So what we're going to do is called quantum phase estimation. So we know that the classical Fourier transform can detect periodicity in a time domain signal. So it can pick out things that are periodic and tell us what their frequencies are. So QFT instead is doing a Fourier transform on the amplitudes of the basis states. So if there's periodicity in the amplitudes of the basis states, we should be able to pick that out with QFT. So one way that we could think about this is if we chose a period t, and we could prepare this state where we have the coefficients in front of the basis states being e to the 2 pi I x over t, where x is ranging from 0 to 2 to the n minus 1. Remember, these are like our spokes on the wheel, where we have t different vectors. And we can see that there's some periodicity here because it's rotating around. Basically, I'm not going to work out the math here. If you're interested in it, you should definitely look it up. But if you apply the inverse quantum Fourier transform to this state, then you're going to measure with very high probability the bit string x1 through xn, which satisfies that 1 over t is approximately that as a binary fraction. So another way to say that is that the measurement result is going to be the n-bit approximation of the reciprocal of the periodicity. So what we've just described is usually phrased in different terms and is called quantum phase estimation. So in quantum phase estimation, we want to estimate a phase theta. So what we want to do is we want to prepare an initial state by taking the quantum Fourier transform of the state that represents theta. And so theta might not be able to be exactly represented with n qubits. So the ket theta is just going to be the n-bit approximation of theta. So just an example, if theta was 3/4, then we can reconstruct theta as 110 because that would be 1/2 plus 1/4 plus 0 times 1/8. But then if you had something that cannot exactly be expressed in 3 bits, like theta equals 1/7, then you would do the closest approximation. So we could do 001, which is going to be 1/8, and that's the closest of the 3-bit basis states. So then if we apply the inverse quantum Fourier transform to the quantum Fourier transform of theta, we should get theta back. And this is how quantum phase estimation works. So in order to do this, we need to construct that state, which is the quantum Fourier transform of theta. So we want to make this state, and one thing that you might notice here is that it's composed of a linear combination of all the basis states of bit strings of length n. And so a good place to start usually in a lot of quantum algorithms is to apply a Hadamard to every qubit, which puts us into the equal superposition state of all bit strings of length n. And that's also a good strategy here. So we're going to do that first, and then we're going to need to adjust the phases of the different basis states. But that's our first step. And then we want to acquire a phase theta k on the basis state k. So we know that we can do this by applying a controlled phase theta times 2 to the j on the jth qubit. And this is going to work because we know that I made this a little, I mixed up two different things here. So I think I was having this be x before. So we can express x in binary. We can just reconstruct it. If there is a 1 in x, we're going to want to apply a phase of theta times 2 to the j. And that is going to add up to give us theta x. So we're going to need an auxiliary qubit to apply our controlled phase rotations. So if we have our auxiliary qubit in the 1 state, and we have a C phase gate, then only when both of them are in the 1 state, it would apply a phase. The first thing that we're going to want to do is apply an X gate to our auxiliary qubit so that our controlled phase gates will be activated. We want to apply a Hadamard to all of our qubits except for that auxiliary qubit. And then we want to loop through all of our qubits and apply a C phase gate, and the rotation is going to be 2 times pi times 2 to the j times our theta. controlled on our auxiliary qubit targeting J. The C phase gate is symmetric, so it really doesn't matter which is the control and which is the target. And then for completeness, we can apply an X gate on the auxiliary qubit again to return it to its original state. So now maybe we can pick theta equals 0.1 to 1/10. And this is what our circuit would look like. Now we can plot the real part of the wave function to see the periodicity, because we know that our phases are going to look like spokes in the complex plane, spokes of a wheel. So if we consider the real part, that's just projecting onto the x-axis, so that should be oscillating as x increases. So let's see. So here's the real part of the amplitude, and then I've also plotted as a vertical line 1 over theta, so that's going to be the period of oscillation. And we can see that that matches with what we would expect. So now we can do the full thing. So let's just pick theta equals 0.1 again. And then the first thing we want to do is our state preparation. And then we want to apply our inverse QFT. So and then this is just a small thing, but we just need to flip the bit ordering at the very end to match convention. So here's our circuit. We have our state preparation section, and then we have our inverse QFT. And then finally we measure all of the qubits except for the auxiliary one. Now we can run the circuit. We'll use the quantum rings sampler, and at the end we'll plot the quasi-probability distribution. So instead of specifying a number of shots, it's just going to tell us what the expected probability is for each of the results. Okay, and we can see that we measured 3 a lot more than all the other ones. And 3 is going to have a binary string associated with it, so that's what we measured in our register. And we printed out here what we expected to measure. So we plugged in theta to this helpful function, which just tells us what we would expect to measure. So we would expect to measure 0.00011 because that's the best binary fraction approximation that we can do with 5 qubits. And that corresponds to k equals 3. So actually we're pretty spot on here. You can also try other things too, so I would encourage you to play around with this and see what you can get. We could also try, for instance, theta equals 0.2. So in that case, we would expect to measure 0.00110, which corresponds to 6. And we can see the result that we get. And we mostly measure 6. So I would encourage you to play around with this, try different numbers of qubits, different choices of theta. And then if you want to challenge, you can also do quantum phase estimation with 2 phases. So for this one, you want to prepare a state which is an equal superposition of the type of state that we just made. So there's going to be 2 different thetas, a theta 1 and a theta 2. And if you do it correctly, you should see 2 peaks, one centered around each of the thetas. That's all for today. I hope you're able to get a sense for how powerful the Fourier transform is, and also how it can play a role in quantum computing. Next week, we're going to be exploring Shor's algorithm for factoring large numbers, and QFT is going to play a critical role in that algorithm. I'll see you then.